Alright, in this video I'm going to talk about the Zermelo-Frankel choice axioms, what axioms are, what assumptions are in mathematics, and all of these other things, and at the end of it I'm going to solve a Millennium Prize problem. Now that isn't a joke, but bonus points if you can guess which Millennium Prize problem we're going to solve. So we're going to start out by reviewing what math even is and what axioms are. So what is mathematics? In mathematics, you're basically trying to prove statements. And the way you do this is you start from earlier statements, earlier mathematical statements or theorems, and you use those and combine them using logic to prove new ones. But if you notice, that process has to start somewhere. And where that starts in the case of most of standard mathematics is with the Zermelo-Frankel axioms. So this gets to a question of what are axioms. The simplest definition is axioms are just mathematical statements, sort of like any other mathematical statement, but sort of how we relate to them is different, because they're mathematical statements that we take as true without having proof. So they're the starting blocks that we use to combine together to prove all of the rest of stuff in mathematics. And so they're things that feel like they should be obviously true. And so there are things like there's an axiom that says the empty set exists, which is more or less saying like any set exists. And there are axioms that say, okay, two sets, collections of things are equal to each other if their elements are equal to each other. And we can have all of these axioms, and the details of what the axioms are doesn't matter all that much, but I'm actually going to say, like, as much as you need to remember them, there are kind of three types of axioms. So the first type of axiom is existence axioms. And these sort of say, well, we're working in some mathematical world. It would be great if things existed at all, because you could make all these rules of what you can do with your mathematical objects, but if there are no objects, then there's not much you can do. So the existence ones, there are two of them. There's the axiom of the empty set, which is this one. So empty set axiom. And then there's an axiom of infinity. And without the axiom of infinity, you could imagine a mathematical world where every object only had up to a finite size. And so these are the only two axioms that you need to start building your entire mathematical universe, with the second type of axiom, which I'm going to call building axioms. So these axioms, now that you have two things exist, you have a set with no elements and you have a set with infinitely many elements, the next thing to do is to start making more stuff. So for example, you have the schema of separation, which lets you do set comprehension. You have the axiom of pairing that lets you go from two sets A and B and get A comma B. You have union. You have power set, the set of all subsets. You have the axiom of choice, which I'll have an entire separate video on. And you have the schema of replacement. And so you'll notice most of these are just rules for how you can take existing sets and make new ones. And a lot of these, like for example, you need union, power set, and replacement to make bigger and bigger infinities. And separation lets you do set comprehension, which is very useful for making certain kinds of sets. And then the third type of ZFC axiom you could call like niceness, or like good properties, or regularity. And so what this says is that our sets kind of behave well. And so the first axiom here, axiom 1 of extension, that says, A is equal to B if and only if every element in A is also an element of B. And so it says equality is determined by the elements. And the other niceness property, well-foundedness, this is secretly the axiom that presents problems like Russell's paradox. The axiom of foundation sort of prevents you from having these logical loops. So there are three types. There are two existence axioms that tell you have an empty set and you have an infinite set. There are 8 axioms that we take as standard that let you, starting with some sets, build new in other sets. And there are 2 nice properties that let you say that everything behaves well, that things don't get weird in your mathematical universe, because without these axioms, you can have weird stuff, but that's an entirely different world. And so what axioms are these mathematical statements that we take to be true in of themselves. They should be simple. They should be conservative. You don't want to assume too much because if you assume too much, like Zermelo did with earlier axioms with an axiom called general comprehension, you could make a contradiction and you could break all of mathematics. But you also don't want to assume too much because you don't want to assume something that isn't true. And this is kind of like a vaguish philosophical notion of like, well, what is true or what isn't true? Is there some platonic idea of what should be true and what shouldn't be? And that's like, there are many arguments about that. But why we are so conservative with the axioms is that, like, okay, maybe we can't tell whether certain things are true, like the continuum hypothesis, but we certainly don't want to make an assumption that leads to some consequences that certainly are untrue. But people have arguments about that, like should the axiom of choice be assumed? And I'll talk about that more in that video because there are some consequences of it that feel untrue, that they feel wrong. And so axioms, there is a bit of arbitrariness, but for the most part, these axioms are strong enough to build all of mathematics. You can do number theory, you can do differential geometry or differential equations, you can do computer science and talk about computability. All of that can be encoded in these sets. And I guess it's useful just knowing that they're out there. Going into the details, even if you're a mathematician of these axioms, is usually not that useful unless you're a set theorist or you're doing something in like category theory where set theory problems come up. But it is good to know that at least there is some foundation and a general idea of how it works. And you can just read this list of axioms and see how it works. Now, the next thing I want to talk about is assumptions. And assumptions, just like axioms, are just mathematical statements. There's, in a kind of technical sense, no difference between an axiom, an assumption, and a mathematical statement. And if you go to Wikipedia for axiom, they'll say axioms, postulates, and assumptions, and they're all the same thing. But really where they differ is that how we as a mathematical community treat them and how we use this language. And so generally, although assumptions are mathematical statements like axioms, and they're mathematical statements that when we use them without proof, the way we feel about them is very different. Usually assumptions are things that we hope to be able to prove later, but can't prove now, but it'd still be useful for it to be true. And so one of the most common assumptions that I've seen around doing mathematical cryptography is the existence of what are called one-way functions. I'll call this assumption OWF. And this is a class of functions that is basically necessary to have any security proof that one-way functions must exist in any of cryptography. And the thing is, one-way functions, the existence of them, if you could prove that they exist, this is a much stronger statement than proving P is not equal to NP. And we're not even close to proving this. Like some people think we're, I don't know, it could be 100 years out from proving P is not equal to NP. And just the existence of one-way functions is so strong that you could prove in one line that P is not equal to NP. And we're going to do that at the end of this video. And the things that you need one-way functions, like for example, just the assumption that RSA works, which is the standard asymmetric encryption scheme, would imply that one-way functions exist. The existence of collision-resistant hash functions that you would use for making something like a proof-of-work scheme, like maybe you're trying to make your own cryptocurrency and you're doing something like what Bitcoin does. That would also assume that one-way functions exist. There's a whole world of lattice space assumptions, so learning with error, or shortest vector problems. And these are basically, we kind of joke that there's only two hard problems that we have an idea about, and that's factoring and lattice problems. And factoring is broken by quantum computing. But these lattice problems, they might be broken by quantum computing. I actually wouldn't be surprised if they are. But so far, we haven't broken them. And so the game in cryptography, because we're so far from our mathematics being able to prove security from the axioms from ZFC, is that we try to make an assumption that is sort of well defended. So for example, this assumption that one-way functions exist is something that we've used for a long time, and we try to base all of our cryptography on that one assumption, so that, over the decades, as this is tested and as many people try to find ways to break it, what we do is that even though our foundation isn't based upon the ZFCs, we have this one extra assumption, say that one-way functions exist, or some things like lattice problems, and that if we can break any crypto system, it would also mean it would break this assumption. And so other assumptions are used in mathematics as well. Like, for example, we have a thing called the generalized Riemann hypothesis, which has to do with these things called L functions. And I actually get these confused sometimes, but there's also a thing called the extended Riemann hypothesis. In my head, these two were opposite from each other. I had the names wrong. And this sort of says the regular Riemann hypothesis is for the integers, and the extended Riemann hypothesis is a similar thing, but for all of these different types of integers. Like, you can imagine the integers where you join I, or if you're looking for details of this, these are things called algebraic integers. And there's actually infinitely many other Riemann hypotheses. And there's a lot of number theory that, who knows how far we are away from proving the Riemann hypothesis or from all of these other Riemann hypotheses, but we can do a lot of math under the assumption that the generalized Riemann hypothesis holds or the extended Riemann hypothesis holds. So assumptions, although they're technically the same as axioms in that they're mathematical statements that when we use them, we assume them without proof, the way we treat them is very different in that we don't think of them as inherently true in of themselves. We think of them things as almost like aspirations or conjectures that we hope to be able to prove later. So going to the next page. Philosophy of axioms. Yes, so now I'm about to contradict and give yet another way to think of axioms. So again, all of these things, axioms and assumptions, are mathematical statements. A third way to think about axioms is that instead of being like, okay, these are things that we think are inherently true, we think of them as like, well, we could imagine a world where they're true. And so this is maybe you could call the philosophically agnostic approach to axioms. So this way, instead of an axiom being, so it's still a statement that is true or taken as true without proof. But now instead we're kind of thinking of it as like, well, instead of taking this as a statement that we really think is true because it's self-evident, we're just saying, well, what if we just imagine a world with a logic with this being true? And so we do that a lot with kind of non-standard examples of things. So for example, there's a way to take the axioms of, say, Euclidean geometry. And one, important axiom in plain Euclidean geometry is if I have 2 points, if I have a line through one, there's one line that's parallel to this line through another point. But you could just have a different axiom for that. You could say, well, instead, if I had a point and I have another point and there's a line, well, maybe there's 2 parallel lines. And then you get to things called non-Euclidean geometries. And the Euclidean geometries. And what you might think is that, well, the non-Euclidean geometry is wrong because I live in the real world, and in the real world, if I have a plane or say I have a flat piece of paper and I draw a line through a point that's parallel to another line, there's only one of those lines. But there are situations where non-Euclidean geometries inherently come up in the mathematical world, and so they're just sort of, we're not thinking of them as the true world, we're thinking of them as a different world. Like, here's a world where non-Euclidean geometries could exist. Other things that one might have, I have listed here Archimedean versus non-Archimedean fields, and this is where you can have things which are infinitely small, and this gives rise to things like, you could have the regular real numbers versus things like the p-adic numbers. And again, one might say it's like, well, the real numbers, they're called real numbers. Those are the real ones. But p-adic numbers, they come up in number theory and all throughout algebra, and they're useful in of themselves, even if they feel like different numbers. Another example that I'll talk about more in the axiom of choice video is that you might have something like if you're doing set theory again, you might throw out the axiom of choice and instead have the axiom of determinacy. And the axiom of determinacy basically says if I have a competitive combinatorial game, what you should picture is something like chess, where two people are making moves, but instead I allow the game to last infinitely long, countable infinity. Is there the axiom of determinacy says all of those combinatorial games, they inherently have one person who always wins. And that's true with finite games, but that's not true if you assume the axiom of choice. And so you can imagine a different world where the axiom of choice isn't true, where the axiom of determinacy is true, and that all of these games hold, that there's always a winner. And in that world, you might have something else, like you might have every subset is Lebesgue measurable. And this is, in mathematics, Lebesgue measurability is kind of how we think of the mass of subsets of like Rn. In practice, when you're doing analysis and you have to do integrals over weird domains, you have to do a lot of bookkeeping, and it's kind of a bit of a headache to keep track of whether you can integrate over some set or some function or not. But in this world where choice doesn't hold, you might not have to do any of that bookkeeping, and maybe there are other properties which are nice. And so this second idea is that instead of saying axioms are things that like we're talking about the real world, like a Platonic idea, we just say it's like, there could be lots of worlds. There could be lots of different ways of doing mathematics, and we just take axioms as our starting block, and we can redo mathematics with any set of axioms. You can come up with your own set of axioms and just see what happens and see if interesting things come out of it. And so that's kind of the two ways you could think of axioms, as the Platonic way and as the game way. Now, what do mathematicians think? I think most mathematicians really think in terms of the Platonic way, that there is a real world of like real Platonic ideas, and we're trying to find axioms that describes that real world. But that we also, when we're doing non-standards things, like say axiom of determinacy or all of these weird axiomatizations, we're thinking of those as almost their own logical objects. And we can think of those as just sort of different logic games that have their own consequences and may be true in that world. And so for the last thing, I'm going to prove P is not equal to NP. Now, this isn't the hardest thing to do. I think the hardest part of this is remembering the definition of a one-way function. So a one-way function, if I remember correctly, is a function f from inputs, which you could call bit strings to bit strings. So this is really like a computable function. You're going from like 0, 1, 1, 0, blah, 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 to other things. Basically inputs and outputs on a computer. And it has this property. If I give it a random input, I'm going to be a little loose here. So I give it some random input and sufficiently random distribution, and I tell someone f of r, then if that person, say that person is polynomial time Turing machine, so a computer that runs efficiently, that also has access to randomness, so it can also flip coins. So we'll put another P for probabilistic polynomial time Turing machine. Then M cannot guess or find inputs X reliably such that f of X equals f of R. So this is the one-way notion, that you can go from an input, a random input, which is important, to an output, and a reasonable machine M will not be able to find an inverse. You could see why this might be useful and how you could start building cryptography out of this. And so now we're going to prove that if we had the axiom of one-way functions exists, we can prove that P is not equal to NP. And the way we're going to prove that is we're actually going to start and do it in the opposite direction. We're going to say if P equals NP, then one-way functions don't exist. So let's suppose we have some function f, and you can compute it in polynomial time. in poly time. And we want to show that no matter what, f is not a one-way function. So we're going to make some computer inv which finds inverses. And here's how we're going to do it. We're going to note that this problem, the predicate f of, we're going to call the predicate p, comma, some outputs, let's call it h. And this problem that says, is there some input r with predicate p, so like let's say this is the first 10 bits, with the first 10 bits of r, such that f of r equals h. This is something that no matter what, this is an NP problem. To go into the details of this, is the reason it's an NP problem is because I can verify that it's true or false in polynomial time. And so, if I have this predicate problem, I can easily find an inverse to any input. So if I start with some x, and I produce an f of x, and then I give that to someone else as a challenge, find some inverse of f of x, here's what they would do. Well, they would check first the predicate under f of 0, comma f of x. Basically say, is there some input that starts with a 0 that if I were to apply f, I would get I would get f of x. And say the answer is no. Well, if the answer is no, then I just check, okay, predicate f 1 comma f of x. And the answer actually will be always yes if I check it for 0, and I get no. And essentially what I will end up doing is I'll do a binary search. So I'll check the first digit, and I'll see, okay, the first digit has to be a 1. And then I'll check predicates for 1, 0, and 1, 1. And let's say I find this second digit has to be a 0. Okay, then I'll check 1, 0, 1, and then I'll check 1, 0, 0. And say it goes down this way. And I'll just keep doing this, checking predicates, until I get an input that's long enough, and this will happen in polynomial time, that gives me some x prime, which might not be equal to x. It might not find this preimage, but it will always find a preimage because 1 exists, x exists, and it will give me an inverse to f of x, and that will prove that f is not a one-way function. And that algorithm gives me an inverter. So if p is equal to np, there are no one-way functions. So if there are one-way functions, p is not equal to np. And I did look up right before this the rules for the Millennium Prize problem. It says, well, it has to be accepted in some journal and it has to be reputable. It's like, well, there's lots and lots of mathematical cryptography papers that assume one-way functions exist. And I think my biggest problem here is that, one, this is an assumption. It's not an axiom. This is not something that we think of as true in of itself. And my second problem is, even if we did think of one-way functions as existing in of themselves, I'm not the first person to notice this. This is something that anybody who does any mathematical cryptography would be able to make this proof sort of off the cuff. And so to review, what are the things to know? I'll go all the way back to the first slide. Well, the first thing to know is that ZFC is a set of axioms that makes up our first mathematical statements that we base all the rest of mathematics on, and we make it out of sets. Axioms are statements that, if we're thinking of them in the Platonic way, they're just things that we think of as self-evidently true, because we have to start somewhere to be able to prove things. We have to start with some statements that have enough power to be able to prove more things, but aren't too powerful that we get contradictions, because early on in Foundations, Zermelo's first textbook he wrote had an axiom that produced a contradiction, and it was a big problem, and so had to kind of adjust things. I talked about the 3 types of axioms. We need that any objects exist, we need to make more mathematical objects, and we need those objects to be suitably well behaved. Talked about assumptions. In cryptography or in a bunch of fields of mathematics, assumptions aren't used extremely often. Sometimes they're often used that say, assuming this, if we can prove this conjecture, we can prove that. But in some mathematical fields like cryptography, to do anything, you have to have assumptions, and so they're used all the time. The second definition of axioms is the non-Platonic way to look at axioms, which is to say, who cares what the real world is? There's a bunch of worlds. We can have Euclidean geometry, we can have non-Euclidean geometry, Archimedean geometries, non-Archimedean geometries. We can do a bunch of stuff. And they're all interesting, and we should look at them, and they are all interesting. And that gives us our sort of two philosophies on axioms. And if you have a suitably strong assumption, you can solve a Millennium Prize problem, $1 million problem, that otherwise, without the assumption, would take maybe the next 100 years to solve. And so that's another reason to be a little conservative with the axioms. So I went over this kind of quickly because I just wanted to give an overview of what axioms, assumptions, and ZFC are. If you have any questions, let me know. I'm just sort of starting out doing this. And yeah, I guess that's it for this one.